Hello, my name is Geunmo Kim, and I would like to introduce the research of our participation in the GENEA Challenge 2023 and the model we used. The table of contents is as follows. While researching trends in human agent research, we noticed that number of features are often used for human agent communication. We decided to participate in the GENEA Challenge, a challenge to generate human gestures using number of features and set the following goals. We aim to utilize number of features and generate natural gestures using two approaches. The first approach applied robot-based word embedding to extract text features, and the second approach used additional features that are highly correlated with gestures. Now let's talk about our research. First, let's talk about data processing. The data we used to train our model was a combination of motion, audio, and text data. For motion, we used the PyMo library to extract motion feature information and an exponential map to represent 3D motion. We also used data from 19 key points extracted from the human upper body and 6 key points extracted from the human lower body. For audio, we used MFDC, MER spectrograms, and prosody, features that are commonly used in gesture generation research, with additional zero crossing rate and rhythmical features that we believe are relevant to gestures. For text, we used robot-based word embedding, as mentioned above, and zeroed out all OOV words for the transcription used to extract text features. We also used additional metadata information, such as a speaker ID and the presence or absence of finger joints. Next, we explain our model structure. Our gesture generation model consists of an encoder and a decoder. The encoder takes input data as one-up vectors and converts them to embedding vectors via word embedding and processes them with 1D convolutional layers and bidirectional LSTM to generate encoded features. We used an attention mechanism to decide which of the features from the encoder to use at the decoder along with the information generated and at the previous point in time. Our model uses locality constraint attention for this purpose. The decoder consists of two pre-connected layers, a ReLU activation function, a one-way LSTM, a fully connected layer, and 5 convolutional layers. It combines the alignment information obtained through the attentions with the gesture features generated at the previous time point to generate the gesture features at the next time point. Our work focuses on the features of the input data. To improve text features, we use the pre-trained robot-based embedding, and for audio features, we used the popular MFCC, MER spectrogram, pitch, and energy with additional zero crossing rate and rhythmical features. Next up are our evaluation results. The results for human likeness are shown in the following figure. Our submission is SC, and as you can see in table 1, we have obtained the results that generate natural gestures in terms of human likeness. To analyze this, we visualized some of the gestures generated by our model using the Blender 3D animation tool. From this visualization, we identified several unnatural gestures, such as the right arm expressing a gesture with fixed position, or the right arm bending behind the head to express a gesture. From this, we can see that our model generated most of the unnatural gestures, which lead to results similar to table 1. Table 2 shows the results of evaluating the appropriateness for speech. The evaluation The evaluation results for the SC submissions showed unnatural gestures that were not appropriate for speech. To analyze these evaluation results, we visualized the generated gestures and examined them. These visualizations showed that we often failed to generate gestures that were appropriate for speech. This, together with the evaluation results, confirmed that the input characteristics we highlighted, genocrossing and rhythmical features, need to be better exploited through preprocessing. Table 3 shows the results of evaluating the appropriateness of generating gestures to match speech when interlocutor information is added. We found that the visualization tended to generate unnatural gestures regardless of the interlocutor information. These results highlight the need to consider interlocutor information to generate appropriate gestures in human interaction situations. From our previous evaluations and analysis, we found that gesture generation based on input features requires preprocessing to match each feature. While we observed mainly unnatural gestures, we have identified potential research directions to improve them. We have drawn the following conclusions from our model and evaluation results described above. Our evaluation of the two approaches to gesture generation resulted in a large number of unnatural gestures, confirming the importance of preprocessing features rather than simply increasing their number. In the future, we plan to conduct experiments using SOTA model, such as the diffusion model, or by varying detailed hyperparameters and conduct gradual experiments by motion audio text features to understand which features contribute to generation of unnatural gestures.